Hello, can you hear me?
Yes.
Okay. Do you also see the screen? Yes, so right. Let me try to write something. Good morning. Is it visible? Yes, I guess so. Okay. So last time what we did is to, so let me recap a little bit. We explained the Boltzmann equation. The Boltzmann equation was basically an equation that allows us to find the distribution function f, which is a function of R and P that is counting the number of particles having a certain position and a certain momentum. And this distribution function depends on R, P, and T in principle. And it basically provides a statistical description of the distribution of position and momenta, both in the equilibrium situation and in non-equilibrium situation. So what is a non-equilibrium situation? Well, something that is evolving in time, and therefore the F depends on time. The equilibrium situation instead is the one corresponding to the case in which the distribution function is stationary, and therefore there's no dependence on time. So the derivative of f with respect to t, the partial derivative, is equal to 0. And if a system is uniform and no external forces are present, that means the collisional integral must be equal to 0. And that provides us the distribution function that you already know, which was the Maxwell-Boltzmann distribution function for the momenta or for the velocities. Then we have seen the so-called H theorem, in which one introduces a sort of entropy. And indeed, the structure of this quantity is very similar to the Gibbs entropy, that is always decreasing in time. And the point at which this entropy, this H quantity is stationary, so does not evolve in time, correspond exactly to the equilibrium condition, because it's the condition for which the collisional integral is equal to 0. Okay, so the Boltzmann equation basically allows us to describe systems out of equilibrium and how those systems evolves towards the equilibrium, and is very much used, for instance, as I said before, in astrophysics, in cosmology, in heavy ion physics, etc. So in all the systems in which thermodynamical equilibrium is not yet reached, or another way to say it is that the system has not fully thermalized. Okay, this is the typical sentence that one uses. Now, there's not much to do for what concerns the applications on the Boltzmann equation, since it is a very complicated equation. One cannot do any analytical calculation, basically. What we actually saw last time is that in the limit or last time, when we reach the equilibrium, we have a distribution function f0, which is just a function of p, in such a way that if I do f0 p times dp divided by the density of particles, okay, I think we derive this quantity. And I remind you that from the dimensional point of view, dn is equal to f0 p dp dr. And therefore, for a system, for the total number of particles will be volume for a uniform system, integral over dp of f0 of p. So therefore, from the dimensional point of view, what is f0? F0 is a quantity that must be, I see from here, this is a density, and integral over dp f0 of p, and therefore this must have the dimension of 1 over volume and 1 over momentum square, momentum cubed. Okay, this is the dimension of f0. And this quantity here in particular was equal to, let me write it in this form as a function of velocity. So let me, as a function of velocity, it was this quantity here. So it was v squared exponential of minus 1/2 m v squared beta dv, and then at the denominator we had kbt to the power of 3/2 m to the power of minus 3/2, and then we have a square root of pi divided by 2. This was the quantity that we derived last time as a function of so which describes the distribution of velocities of particles, where beta is 1 over kbt. Okay, now how did we obtain this distribution function? Well, we basically assumed that dp in spherical coordinates was 4 pi squared dp. Therefore, we have integrated, if you want, over the solid angle, and so this holds true for spherically symmetric system, no? So for spherical symmetry. Okay. Now, what I want to do now is to make an exercise, to present you an exercise which basically makes use of the Maxwell-Boltzmann distribution for the velocities, but in a slightly different situation. Here we are talking about a system in a volume V with a certain number density, a certain temperature, and we have a distribution of velocity which is provided by the formula that I just described. Okay. I mean, the most important thing is to remember the exponential factor, which is very easy to remember, and the fact that I have a v squared dv, which comes from the basically spherical coordinates. All the stuff that is in the denominator is basically providing a sort of normalization, if you want, okay? Now, the system that we want to describe as a sort of exercise is the following. Suppose that instead of having a volume V which is closed, we have a volume with a small hole here. So here we have the particles. And we have a small hole, very small. What it means very small. So let me put, first of all, an axis here. This is zeta versor. The size d of this small hole, d, is much smaller than the lambda, which is the mean free path. What is a mean free path? Is basically the path that a particle is covering, the distance that the particle is covering between two collisions with two other particles. Okay, so this is the, let's say, free streaming distance that is covered by a particle. Okay, and the very much smaller than the mean free path is our assumption, which is basically telling us that when a particle is close to this hole, basically it can flow across this hole without any other collision. Okay, this is a very important remark, because this is the condition for having what is called effusion. Okay, so the particles that are exiting the box are, let's say, a sort of sample of the particles of the whole system, as we are going to see in a moment. Indeed, the exercise is to find the flux of particles which exit the box. And once we determine the flux, we can determine the average. So first, this is the first question, if you want. Second question is the average velocity and most probable velocity. Among the particles that are flowing out. Streaming out. Okay, so those are the two questions we will try to answer by using the distribution function that we have found last time, which is something that you already know, which is the Maxwell-Boltzmann distribution function. Let me change page. First of all, let me write the following quantity. For the distribution function that we just described, we have integrated, if you want, over the solid angle. But here now, we cannot integrate anymore over the solid angle because we have to select the particles that exit this hole, this zeta versor. And therefore, the infinitesimal flux, let me call dj, this is infinitesimal flux of particles streaming out is equal to v cos theta. Well, if you want, is v the velocity scalar zeta versor. And if I introduce the spherical coordinates, so this is the zeta, this is a velocity v, and this is the theta. So this is actually v cos theta times the distribution function that we just wrote, but not integrated over the solid angle. Okay. So this infinitesimal flux must be something like v scalar z. I will come in a moment on this. And then we have the Maxwell-Boltzmann distribution, which was provided before, which was proportional to the density. And then we have the factor, which is m divided by 2 pi kbt to the power of 3/2. Then we have the exponential. Well, we have a b squared, then the exponential, and then we have a dv. Then we have d cos theta d phi. So this is the solid angle. Okay. Let me check if this is correct. And then I have a b squared m divided by 2 b kbt dv d cos theta d phi. So basically what I have done is to take the previous expression that I just wrote and dividing by 4 pi because I'm not integrating over the solid angle. Okay, so take the previous one and divide by 4 pi in order to eliminate this integration over the solid angle, because now we cannot integrate over the whole solid angle. Okay. we have to be careful now when we integrate over the solid angle, because we have to take just the particles that have the right sign of the velocity, well, the component of the velocity which is exactly along the z-axis. That's why we are introducing this v scalar z. Okay, so dj can be written, once we introduce v cos theta, as well, is n velocity cubed m divided by 2 pi kbt to the power of 3/2, the exponential, and I have a dv, then I have a cos theta, d cos theta, d phi. Let me check if this is correct. Okay, dv cos theta, d phi, d cos theta. Okay. Now, this is the infinitesimal flux, which is not integrated over the solid angle, okay? Now, let's make the integral over the solid angle. So let us integrate over the omega, and therefore we have a dj. Actually, this will be a, let me see, 1, 2, 3. This will be a d3 if you want, but let's, okay, I mean, usually we are just integrating over d cos theta and d phi, and this will be still an infinitesimal flux, which is just integrated over the solid angle. So let us integrate over the omega without having this heavy notation of lowering the dj3 to dj1, okay, to 1 dj. So let us integrate over the solid angle, and we still have a dj, which is now integrated over the solid angle, which is n v cubed m divided by 2 pi kbt to the power of 3/2 exponential v square beta, and I have a dv, and now I have to do this integral. So I have to integrate over d phi from 0 to 2 pi, as usual. Then I have to integrate the cos theta or d cos theta. Now be careful here, you have to integrate between 0 and 1, not from -1 and 1. Why? Because theta cannot vary between 0 and pi, because theta belongs to the interval 0 pi squared. Okay, why? Because I have to select all the particles that they have a component along the z versor. Okay, so a velocity component along, otherwise they cannot exit the box, right? They have to have a component of velocity along the z, which is positive. That's why I'm integrating from 0 to 1, okay? So now this is equal to 2 pi in this case, whereas this is equal to x squared half, so this is just 1/2, the second integral. So then the dj, now integrated over the solid angle, is n pi, and then I have a v cubed, the normalization m divided by 2 pi kbt to the power of 3/2 exponential beta n dv. Okay, now let me make at some point it's good to have a dimensional analysis in order to check if our calculations are correct. So let me make this dimensional analysis in order to be confident that is indeed a flux of particles. So let me write again this dj. dj is equal to n pi. Sorry, I have to change page. Gj is n pi, then I have m divided by 2 pi kbt to the power of 3/2, and then I have the exponential, I'm not going to write, v cubed dv. Now let me see the dimension of this quantity. N is a dimension 1 over length cubed. Then I have v cubed dv, which should be a length to the power of 4 divided by time to the power of 4, because it is a velocity. And now let me take the nasty part, which is this one. I have kbt. Remember that kbt has a dimension in such a way that kbtm has a dimension of momentum squared. So if you want how to do it, well, okay, just as a rule, just put K. Remember the kbt is an energy, okay? So it's something like p squared divided by 2m. Therefore, mkbt is a momentum squared, as I said before, momentum squared. I think you cannot see. And therefore, here I have a mass, and so here I have a mass inside to a power of 3/2. And then we said that kbt times the mass is a momentum squared divided by the mass. So kbt has a dimension which is mass squared, length squared divided by time squared, and divided by the mass. Okay, so it should be ml squared divided by t squared. ml squared divided by t squared, if I done it properly. I hope this is correct. So the mass and the mass drops. Then I have, let me see here, I have T, yes, so I have L4, L3, 3, so 1 over length squared, and then I have 1 over time, yeah, so it's because this will be t to the power of 3 at the numerator, and then a t to the power of 4 at the numerator. So it's 1 over length squared divided by time. And indeed it is correct. Okay, so it's the number of particles divided by a surface times time. Okay, so this is correct. It is a flux. Okay, it's a flux of particles. Now, sometimes it's useful to have a sort of how to say dimensional analysis in order to check that everything is correct. Okay, so it's boring, but it's useful to do it. Okay. So now this is the flux of particles in which we are not yet integrated over the velocity. So now let us integrate over v, so the velocity, to obtain the total flux, so integrated over the velocity, which is something that is useful. Now, this point, we can call it j, and this j is equal to the integral over dj from 0 to plus infinity, which is the integral from 0 to plus infinity of the quantity that I just found, which was n pi. Then I have m divided by 2 kbt to the power of 3/2, exponential of 1 minus m v squared beta, v cubed dv. Okay, equal Let me put outside all the numbers that do not depend on the velocity. So I have n pi, then I have m divided by 2 pi kbt to the power of 3/2. Then I have the integral from 0 to plus infinity of the exponential v squared beta v cubed dv. And now let me do the following trick. There is an equal here missing. I don't know why. Missing this equal. Let me do the following trick to multiply and divide by 4 pi. Now, why I'm doing that, for a reason that is going to be clear in a moment, let me just put out this. Questo qui non ci serve. 4 pi, and 1 divided by 4 pi. The thing is that if I introduce the average v, so the average velocity, from the Maxwell-Boltzmann distribution, this average velocity should be something like this. Should be m divided by, well, the usual 2 pi kbt to the power of 3/2. Then I have a 4 pi that comes from the integration over the solid angle. Then the integral in dv from 0 to plus infinity of v squared that was present in the distribution times v, that therefore I have a v cubed, and then the distribution function, which was the exponential. Okay, so this is the average velocity, let me say in the bulk, which comes basically from our distribution function of the velocity multiplied by v. Now, if I have to find an average, I have to multiply by v. Okay. So in this respect, I have the quantity that is here. It is just the average velocity divided by 4n times n. Okay, because I now simplify pi and pi, and what I have here is just the average velocity, and then I have an additional factor 1/4 times n. So that means that J is nothing but 1/4 n v average. Okay, where v bar is the average velocity in the bulk. In the bulk means inside the box, okay, not close to the hole. Inside the blocks, this is the average velocity, and this is the total flux is n average velocity divided by 4, okay? Of course, the flux inside the box will be just n v average, okay? So these are divided by a power, by a factor of 4. Let's try to compute the average velocity so that we have an expression for that. So the average velocity, we said, is m divided by 2 pi kbt to the power of 3/2. Then I have 4 pi, which comes from the solid angle. Then I had, let me introduce a variable that I call, well, actually I don't need it. So this is 0 plus infinity. Then I have a v cubed exponential of 1 minus, well, let me call this v squared times alpha, and dv, where alpha is defined to be m divided by 2 kBt. Okay. Now this integral can be done. Of course, I'm not going to do it. It's boring, and you can do it by parts or with Mathematica. And this is equal to 1 over 2 alpha squared. Therefore, the average velocity will be m divided by 2 pi kBt to the power of 3 half. And I have a 4 pi. Then I have 1 divided by 2, and then I have 1 divided by alpha squared, which is 4 kBt squared divided by m squared. Let me see if this is correct. So this is the average velocity. So it's m, 2 kBt, 4 pi, blah, blah, blah. Okay. Now, if you work out a little bit this square root and this 3 half, you see that there is a kBt squared and then a kBt 3 half at the denominator, which will be 2 minus 3 half, which is 1 half. So you have a kBt at the numerator. So work out a little bit this expression, is just algebra, and you will get 8 kBt divided by m pi. And this is the average velocity in the bulk. Okay. Now, you can notice one thing, and then we go to the flux of particles that are going out, streaming out of the box. But first, since we are talking about the average velocity in the bulk, there's something that you might have obtained already in the past. We can notice that V bar is different from Vp, where Vp is the most probable velocity. This is due to the fact that the distribution of the velocity of particles is asymmetric, is a v squared times the exponential of minus something v squared. The most probable velocity can be computed indeed as follows. I have to take the derivative of v of my distribution, which was a v squared exponential of minus m v squared beta, and put it to 0. Which means 2v exponential of blah blah. Then I have a minus v squared, the exponential, and then I have mv beta. Mv beta should be mv beta. Now equal to 0, you remove the exponential, you can remove a v, so you have 2 minus v squared m divided by kBt is equal to 0, and therefore the Vp finally is equal to 2 kBt divided by m square root. Okay, 2 kBt divided by m square root. 2 kBt divided by m. Okay, so you see that the most probable value and the average value in the bulk, this is again in the bulk, they are different, as you might remember from General Physics 1. I don't know if you have done this calculation. Now let's do the same for the flux of particles streaming out. So which are V and Vp for the particles streaming out. just to make a comparison. Now for VP, we follow the same procedure. It's just that now we have to derive, with respect to the velocity, the distribution of particles streaming out, which is not a power of v squared exponential, but v cubed times the exponential. And then you put this equal to 0. Now the calculation proceeds as before. It's just that you have now a 3v squared times the exponential minus v cubed exponential, and then you have m v beta, so kbt if you want, from which you get the average, so the most probable value of the for the particle streaming out is now 3 kbt divided by m. Okay, so this is larger with respect to the one in the bulk. Another thing that one can do, and we do it, is to compute V average again for the particle streaming out. And this V average basically can be computed as follows. Let me write in a correct way. I have to take what was the infinitesimal flux, integrate over V, and so therefore I have this factor which were outside, 2 pi kBt to the power of 3/2, and integral from 0 to plus infinity of, well, here I had V cubed, the exponential, and here I have to have another V if I want to compute an average, no, because this was the distribution. Then I have a dV, and a denominator I have a normalization, which is n pi m divided by 2 pi kBt to the power of 3/2, then 0 pi. Well, this is actually the total flux, no? Which was V cubed exponential V squared beta, and then dV here. Now, of course, again, it's boring to do this integral. That can be done. Of course, this part will cancel, so this is not a problem. And once you do the calculation, well, this can be written as follows. So integral over 0 to plus infinity of dv v to the power of 4m e to the minus alpha v squared, and a denominator I have 0 plus infinity dv v cubed e to the minus alpha v squared. Now you can show, for instance, by using Mathematica. So this we said already that is 1 over 2 alpha squared, whereas the other integral is the following, is a square root of 9 pi divided by 8, and then I have alpha to the power of 5/2 times these 2 alpha squared. Okay, and you work out a little bit the details. You substitute alpha with its value as before, and then you get that the average in the bulk, average for the particle streaming out is 9 pi kBt divided by 8m. Okay, so what you see is that basically in the bulk we had the Vp and V average were respectively, let me write it back, so Vp was square root of 3 kBt divided by m, whereas the average was...
Scusi.
Sì, non ho cambiato foglio, certo. Ok, grazie. Bulk, Vp and V average. The Vp was 3 kBt divided by m square root, whereas the V average was 2 kBt divided by m. Okay, So this was in the bulk. Now in the particle streaming particles, so particles streaming out, we just derived that Vp, I guess I'm not doing a confusion. Sorry, this was 2 in the bulk. I'm making a mess, sorry. Sorry, I'm making a mess. Sorry. So in the bulk, Vp and V average were respectively, Vp was 2 kBt, 2 kBt divided by m, and the average was 8 kBt divided by m pi. Okay, these were the correct values in the bulk. Let me check again. 8 kBt, m pi, and 2 kBt. Okay. Whereas for the particle streaming out, we have that Vp is 3 kBt divided by m, and the average is 9 pi kBt divided by 8m. 9 pi kBt divided by 8m. So what happens is that both the most probable values and the average values are larger with respect to the bulk quantities. Therefore, this setup, so you have a box with a small hole. I remind you that small means that the size of the box the size of the hole must be much smaller than the mean free path. You basically select the high velocity particles. Okay. Well, actually, as you see, for the v squared, so for instance, the average velocity squared as 1 over m, over square root of m. Therefore, if you have two components, one with mass m1 and the other one with mass m2, the ratio between the average velocities of these two components will be v1 average, v2 average, scales as the inverse of the square root of the mass, no? Therefore, the smallest particles, so the smallest, the lighter the particle, the larger the average velocity. Okay. And indeed, a fusion is used to select, to distinguish, for instance, well, or to select high velocity particles. So, or actually to separate components. Okay, so this process, which is a fusion, let me change page. So a fusion allows to select, or to separate, better to say, components. Okay. By using the hole and the fact that the particles with the smallest mass will have a higher flux, okay, and higher velocity as a consequence. Okay, so remember that this was obtained by assuming that the mean free path and the size are in this relation. So the size of the hole must be smaller than lambda, okay? because otherwise, if the size of the hole is as large as lambda, basically there's no any selecting effect. So the distribution of particles going out will be just the same as the particle in the bulk. Okay. Okay, so this was just an example on, for instance, how to use the Maxwell-Boltzmann distributions for the velocities. Remember that you have a v squared exponential of minus, well, the kinetic energy beta in the bulk. So this is the distribution in the bulk. Whereas in the streaming out particles, the distribution is a little bit different. There is an additional power of velocity, v cubed. Okay, so that's just the difference. Okay, distribution in the flux of particles. Streaming out. Okay. And also another thing that could be useful to do once a while is to do a sort of dimensional analysis in order to check that everything you are doing is correct. Okay. Now let me close this part of the course and let's start with another topic. Let me just introduce the topic and then we make a break. Actually, these can be also removed. No time to do this. And the next topic is the ensemble theory, which is basically the hardcore of statistical mechanics, which is ensemble theory. The ensemble theory is basically a the construction of statistical mechanics thought by Gibbs. Okay. And the idea is the following. Suppose that we have a system. Now we are not talking anymore about systems which are independent and localized, as the examples that we have done in the last weeks, in which, for instance, we had a certain number of particles in certain spectrum of energy levels in which we were distributing particles. This is a system of independent and localized particles, which is very useful for making examples, but is not very realistic. We want to describe a situation which is more realistic, in which we have particles that can have the freedom to move in space. And so we basically have three quantities at the beginning, which is volume, number of particles, and E is total energy. Now the total energy is a quantity that you will see just at the beginning, what is called microcanonical ensemble, and that will be substituted by the internal energy. The difference is, as I said already a few times, is the fact that where E is a classical mechanics quantity, and it is a conserved quantity, whereas the internal energy is a thermodynamical quantities for which, so that is basically defined only at the thermodynamical equilibrium and which can fluctuate, whereas E, which is the total energy, is a quantity that is fixed. It cannot change if there is no energy leakage or a source of energy in our system. So if you want, you can think about a system which is completely isolated. It has a certain volume, certain number of particles, and a fixed total energy. Now, those are variables which are macroscopic: the total energy, total volume, and total number of particles. And suppose that omega is the number of microstates compatible with having a system with fixed energy, fixed volume, and fixed number of particles. Okay, compatible with E, V, and fixed. Well, of course, the number of particles fixed is not very interesting, but what is interesting is the energy and the volume, and you will see why there is a degeneracy. It will be clear in a moment why there is a degeneracy between number of microstates, between microstates which are compatible with the microscopic constraints of having fixed energy, fixed volume, and fixed number of particles. Now, our system, if you want, moves along different microstates as a function of time. Okay, so as a function of time, the system, if you want, moves or change its microstate. You will be clear in a moment what is a microstate, but in principle you can change it as a function of time. And suppose that F is an observable.
Prof, il foglio, scusi.
Non ho cambiato il foglio, ormai questo è il mio vizio. Suppose that F is an observable, which means a quantity that can be measured, macroscopic quantity that can be measured. And we can define a sort of average of F, time average. As this sort of integral. I have 1 over tau, t and t plus tau, and then I have f t dt. Because since the system is changing states, f will be a function of t. The system is changing its microstate, and therefore every quantity in principle and every observable quantity is itself a function of time because the system is changing its microstate. But we are not interested in what this quantity is doing as a function of time. We just make a time average, where tau is called relaxation time. Which we take as a time to do an average. Now, of course, what is this procedure is to basically what we do when we measure, for instance, I don't know, the pressure of a gas. We basically use some tool some measuring apparatus that allows us to measure the pressure. And of course, when doing that, the system what is doing is collect, if you want, a certain number of. So it's taking it needs let's say sort of interval of time in order to measure, for instance, the pressure or other quantities. Is not a instantaneous measurement, because there's no meaning on that, no. So you put your instruments in contact with your system. You wait for a while. This relaxation time basically is the time to measure, if you want. By not considering all the possible fluctuation that could happen as a function of time, and then you average over this time. Okay, so this is basically what we are doing in practice when measuring an observable, a macroscopic observable for a system of multi-particles. That could be the pressure, could be the temperature, it could be the everything, the volume, etc. Okay, again, for the temperature, when you put your thermometer in your system, you need to wait a sort of relaxation time in order for the system to get to interact with your thermometer, with your measuring apparatus. No, so this relaxation time, if you want, in that case, this time is the time you need to measure the temperature, for instance. No. And in doing that, what you actually are doing is to probe, as the function of time, many possible microstates, because the system is not in a fixed microstate. Its microstates are changing as a function of time. When you measure, you're sort of doing an average over time of a certain quantity that depends on the microstates. Okay. Now, the main hypothesis under statistical mechanics, and in particular, so in this ensemble theory, is that actually this average over time can be substituted, which is something that is difficult to compute from the theoretical point of view, is something that can be substituted by an average over an ensemble. Okay. So instead of averaging over time, we make an average over an ensemble. What is this ensemble? Ensemble means a collection of copies of our system having or occupying, each of them occupying a single microstate compatible with the EVN constraints. Okay, so I will write a collection of copies of our system occupying all the possible microstates compatible with having EVN fixed, which is the quantity that I was introducing before, this omega. So this average now will be substituted by an ensemble average, which is 1 over omega, which counts the number of microstates compatible with EV and N fixed. And here you have a sort of sum of Fi, where this Fi and this sum is a sum over the microstates. Okay. Now here there is hidden an hypothesis which will be important also for the rest of well, I will come back to this hypothesis afterwards, But here we are implicitly assuming that all the microstates are equally probable. Because I'm not introducing at this level a sort of distribution function for the microstates. I'm just summing over all of them. So I compute for all of them the quantity f, which depends on the microstates. I'm summing over them, and then I'm dividing by the number of microstates. Now, this procedure is the basis of what is called microcanonical ensemble, and we will come back to this in a moment. But actually, we have seen already something similar in the past, which was the situation we have analyzed in which we had certain number of particles with k possible states, and at some point we said that at the thermodynamical equilibrium all the states are occupied with the same probability, which was 1 over k. Okay, so you might remember this. And here is the same. So in that case, we say that all the possible states are equally probable, and the states were k possible states, 2 in the case of a spin 1/2 particle, for instance. Whereas here, we are talking about something which is a little bit more complicated, which is a microstate, and we will see now how to define the microstate, where we are saying that basically all the microstates are equally probable. Okay. Now, to be more clear about what a microstate is, let me change page. Now, let's set up our system. So first of all, we are in classical mechanics. At least at this level. And we have, as I said before, E, V, N are the quantities which are total energy, volume, and total number of particles. We can define gamma as a phase space, which is different from the mu space that we introduced for the Boltzmann equation, because the mu space was a space in momentum and position of a single particle, whereas the phase space is basically the space of all the coordinates in the Hamiltonian description of a classical system. So I have 3 n values, or well, 3 n variables q I, which are the configuration or the positions, if you want, positions. Qi could be, for instance, qx, qy, and qz for a particle 1. Then could be q2x, q2y, q3z, q2z, etc. Okay. So I have 3-dimensional space. For each position, I need the 3 variables, and then I have a total of 3n, n number of total positions, if you want. Okay, for n particles, I need the 3 quantities in order to fix the position. And similarly, I have 3n variables of the type pi, which are the momenta of the components of the momenta. No? So again, this will be p1x, p1y, p1z, p2x, p2y, etc. Okay. And now a microstate. What is a microstate? A microstate is basically a point in the space gamma, which is the phase space, which means basically a collection of values, fixed values of Q and P. And by Q and P, I indicating the vector of these 1, 3, and numbers in both cases, okay? And if I want to do a plot, suppose that I have, of course, here we'll have a 3n axis, so 6n axis actually. Let me put here P and Q, and a microstate will be just a point here, which is determined by Q, which is a function of T, and P, which is a function of T. I'm pretty sure that you are used to this kind of formalism from analytical mechanics, okay? So also to phase space. So this is a microstate, is basically a collection of position and a collection of momenta for all our particles, which of course must be compatible with having a total volume V, total number of particles n, okay, this is already implicit, and specifically the total energy must be E, must be fixed to E, okay? Now we have the Hamilton equations that allows us to write how the microstate is changing in time. And this is basically a system of equations which is the following. Qi dot is the partial derivative of the Hamiltonian with respect to Pi, and Py dot is minus the derivative of the Hamiltonian with respect to Qi, where H is the Hamiltonian, which is actually coincident with the total energy for a classical system. The Hamiltonian can contain kinetic terms and potential terms and so on and so forth, okay? So, same page again, as a function of time, if I have at a certain time here, I have certain il foglio, certo, grazie, P and Q. Suppose that I have an initial state here with certain Q of T1 and P of T1. The Hamilton equation, mancano gli assi. The Hamilton equations allows us to evolve this point along a trajectory, okay? Here we'll have a Q of T2 and P of T2, and this is a trajectory of my system in the phase space, gamma, okay? So basically from a mechanical, so macroscopical point of view, the system is described by a collection of 6n numbers, which corresponds to the coordinates and the momenta. The evolution of the system in time is made by the Hamiltonian evolution. Once I know the Hamiltonian, I can compute, which is the temporal evolution in time. So therefore, everything could be computed in principle, of course, from a microscopical point of view, because in principle, I also know, if I know the Hamiltonian and I know the initial condition, in principle, I can solve all these 6n differential equations, and I can compute what is the function f of t, and then in principle also compute the time average. Of course, is needless to say, this procedure is not affordable. So to solve all these equations, and is also not interesting and therefore one has to develop a technology which is alternative and which basically provides something which is interesting without doing all these 6n, without solving all these 6n differential equations. Okay. Now a couple of notes, and then I will stop for a break. First of all, the trajectories do not have intersections, self-intersections. So no self-intersections. So something like this cannot happen. Why in that case I have a bifurcation? So so in this point I don't know where to go. So if I have to go here, if I have to go here in time, unless I have a periodic trajectory. Unless I consider periodic motion, such as, for instance, an harmonic oscillator in one dimension, 1D harmonic oscillator. That will be something like this. The trajectory PQ will be something like this, okay? For harmonic oscillator. So there is a periodic trajectory. 2, notice that E and V are fixed, and that means that I cannot change as much as I want the momentum of a single particle or the position of a single particle, no? So I have a maximum and a minimum for all the Qi and the Pi. So the Qi and Pi have a maximum and a minimum. Well, the minimum of Pi could be 0, of course. The maximum is the one which is, of course, not very reasonable, in which all the energy is carried by just one particle. But okay, of course, this has to be considered, but of course, the real maximum will be much smaller. And similarly for the position, since I have a volume, a fixed volume, I have a certain, I have constraints over the possible values of the position of the particle. Okay. Well, actually, the fact that the energy is fixed, since E is fixed, the trajectories, me ne sono accorto da solo questo giro, since E is fixed, the trajectories will lie gamma would lie on a hypersurface in which H is equal to E, is the fixed energy hypersurface. Okay, so this is basically a surface in which you can have the trajectories, since the energy is fixed. So you have one constraint over the energy, which turns into an equation of this type, no? I is equal to E. In principle, you have a trajectory over all the volume of the phase space, which can somehow occupy all the possible values in the phase space. But actually, since you have a constraint on the fixed energy, That's the motion or the trajectory evolved along a hypersurface. Okay. Well, I think I will stop for a moment because it's 12:20, and I promise you to make a break, otherwise it gets very heavy. So let's gather again, let's say 5 minutes or so. Okay. Okay. Don't know if I can continue. May I proceed? Okay, I will continue in any way. I think we are recording this, so in case. So now the thing is the following. Suppose that we have a certain point in phase space here with certain coordinates qi of t and pi of t. Now for sure there will be this point corresponding to a single microstate compatible with the macroscopic constraints. For sure there will be infinite number of points which are pretty close to this one that corresponds to the same microstate. There are infinite number of points close to qi of t and pi of t, which would correspond to the same macrostate. Okay. If you change, for instance, if you switch the position of two particles, or you change the momentum of one particle of a certain quantity and of another particle by say the opposite quantity, of course the total energy will be the same, no? So there is an infinite degeneracy over the microstates that corresponds to the same macrostate, okay? And this allows us to introduce a distribution function in phase space, rho, which is a function in principle of all the qi, the pi, and in time. And this is a distribution function in the space gamma, which is the phase space, such that if I do the rho of qi, pi, t times the differential dq3n dp3n, this provides the number of microstates compatible with the constraint with the macrostates, with the same macrostates, compatible with the same macro state, which was the one with a certain energy E, volume V, and number of particles N. Okay. Now, this is the main, the distribution function in phase space is the basically quantity that contains all the information we need. Actually, this distribution function is much more rich and complicated with respect to the distribution function of the mu space of the Boltzmann equation, because in that case, it was a single particle distribution, whereas this one is a distribution that depends on over the momenta, over all the position, and on time. Now, suppose that we have F, which is an observable, and F in principle depends on Qi and on Pi, and so it depends on the microstates, no? On the microstates, and implicitly depends on time. Therefore, what we had before as an average becomes this ensemble average now can be written in a more reasonable form. So the ensemble average now is this one. I have a function f, which is this observable, which is a function of qi and pi. Then I have the distribution function, rho of qi, pi, and t, in principle, d3q, d3nq, d3np, divided by a normalization, which will be rho of qi, pi, t, d3nq, d3np. Okay, so the average, the ensemble average that I was introducing before, which was substituting the time average, now has the following form, where I am introduce a distribution function rho. Okay, actually rho characterizes the ensemble and actually can be confused or can be substituted with the word ensemble. So rho is the fact the ensemble. And we will see that we will have three possible ensembles that we will use: the microcanonical, the canonical, the canonical ensemble. And we say that the ensemble is stationary when the partial derivative of rho with respect to time is equal to 0. The ensemble depends always on qi and pi, so it has an implicit time dependence, but it is stationary when the time dependence is not explicit. That is something that we expect at the thermodynamical equilibrium. In thermodynamical equilibrium, we have of course, there is some dynamics. The qi, the pi will change in time because there is an Hamiltonian dynamics. The rho, so the distribution function depends on qi and pi, so there is an implicit dependence on time, but there is no at the thermodynamical equilibrium, there cannot be an explicit dependence on time, so rho must be stationary. Okay, there's no direct time dependence, at least at the thermodynamical equilibrium. Now we will see that rho is the solution of an equation, of a continuity equation, which is which expresses the Liouville theorem. And I think that after that maybe it's over. Now, suppose that we are in phase space. This is P, this is Q, and let's take a region, a portion of the phase space with a certain volume omega, and the surface that is called sigma. Okay, this is omega, and this sigma is the surface of this portion of the phase space. Now here in this omega contains a certain number of elements of the ensemble. So all let's say the representative points of the ensemble. And the variation in time of the ensemble points is provided by the following integral. If I do the partial derivative of, with respect to time, of the integral of rho in d omega over omega, where d omega is d3 and p, d3 and q, this is basically the variation in time of the number of ensemble points that are inside the volume omega. Okay. Now we can compute the variation in time in terms of flux also. So the flux across the surface sigma will be something like that. Would be the integral, the surface integral of rho v scalar n versor d sigma, as usual when defining a flux, where v is a vector of a 6n dimension that contains the qi dot and the pi dot. Okay, so rho counts the number of states within it's a phase space density. If I multiply rho times a velocity, and this is a flux in phase space, and then if I multiply by a surface in phase space, which is this d sigma, this is basically a number of states as a function of time. Okay. Now, this is equal by using the divergence theorem to the integral over omega of the divergence of rho v integrated over the volume omega. Now, if the total number of points is conserved, if the total number of points belonging to the ensemble is conserved, which means basically that I'm not losing trajectory in my volume. So basically, if I have this omega here, and then I have a trajectory here, then the same trajectory is exiting. Okay, so I don't have an accumulation or a leakage of trajectories inside this volume of the phase space. Okay, so what enters goes out, or nothing basically originates from this volume. Okay, it's just the trajectories are there is a flux of trajectories crossing this volume. Okay, now if the total number of points on the ensemble is conserved, so that means I'm not losing or not creating trajectories, then the derivative with respect to time of rho d omega must be equal to the flux, the integrated flux, so to minus integral over omega of the divergence of rho v in the omega. Okay. Therefore, from this, I get a continuity equation, which is a standard continuity equation that is telling us that the derivative of rho with respect to time plus the divergence of rho v is equal to 0. This is a standard continuity equation which describes, as usual, the conservation of something. Okay, could be conservation of number of particles, conservation of charge. For instance, you have a continuity equation which basically is the divergence of the density current, which is equal to minus the derivative of the total of the charge density. So it's a very standard continuity equation which is applied to the number of trajectories or the number of points in the ensemble, if you want. Okay, now let's work out a little bit this equation as follows. So now here I have the partial derivative of rho with respect to time, plus when computing the divergence of this quantity, I have to do the following. I have a sum over from I1 to 3n of the derivative, partial derivative of rho with respect to qi dot plus the partial derivative of rho with respect to pi dot, where I'm computing the gradient of rho and multiplying the gradient, so scalar, I'm doing a scalar product with the velocity. Okay, so here this differential operator is acting on rho, plus then I have a rho sum from 1 to 3n. Now you have the derivative of the velocity components with respect to qi and pi. So you have the derivative of qi dot with respect to qi plus the derivative of pi dot with respect to pi. And this must be equal to 0 for continuity. Now this is equal to 0 because q dot I is the derivative of the Hamiltonian with respect to pi, following the Hamilton equation, whereas the pi dot is minus the derivative of the Hamiltonian with respect to qi. Okay, and therefore this basically corresponds to the mixed okay, if I do now the derivative of qi with respect to qi, this is a second derivative of h with respect to qi and pi, and the derivative of p dot I with respect to pi is the mixed derivative with respect to pi of h. Okay, now what I'm doing, what I have in the bracket is just the sum of the mixed partial derivative, no? Sum of basically second derivative of h with respect to qi and pi minus the second derivative of h with respect to pi and qi, which is of course 0. And similarly, go a change page, the derivative of rho with respect to time plus, now I can use again the Hamilton equation to write the d rho with respect to qi. Qi dot is the derivative of h with respect to pi. Then I have a minus derivative of rho with respect to pi and the derivative of h with respect to qi. This is equal to 0. Now, in a more elegant way, this is the partial derivative of rho with respect to time plus the Poisson bracket of rho and h. This equation here is called the Liouville theorem. And it might be that you have done it in classical in analytical mechanics, but I'm not sure about that. Okay, it's basically a sort of continuity equation, which can be then, by using the Hamilton equations, can be written as a sort of total derivative, no? Because this is actually the total derivative with respect to time or rho. The total derivative in Hamiltonian mechanics is the sum of the partial derivative plus the Poisson bracket. And this is general, okay? This equation is general, so it holds true in general. That means equilibrium, but also non-equilibrium situations. Okay, so it's a general equation for rho that holds true in general. Okay, both in the thermodynamical equilibrium, but also out of thermodynamical equilibrium. Now, the thermodynamical equilibrium for us in this context, thermodynamical equilibrium is always characterized by the fact that our system, although it has a microscopic dynamics, on the macroscopic point of view is stationary. So thermodynamical equilibrium means for us in this context, in the context of ensemble theory, that the partial derivative of rho with respect to time is equal to 0. So that the rho is stationary with respect to time, although it depends implicitly, of course, on the single pi and the single qi. Okay. which by using the Liouville theorem means that the Poisson bracket of rho and h is equal to 0. Okay? And now, so one has to analyze the situations in which the Poisson bracket between rho and h is equal to 0. Well, there are different possibilities. We will actually analyze 3 different possibilities corresponding to the 3 different choices of rho, and therefore to 3 different kinds of ensemble. The first ensemble that we introduce, and it allows us to basically solve trivially this equation, is the so-called microcanonical ensemble. Microcanonical ensemble, in which case rho does not depend on T, as it should be if you want to describe thermodynamical equilibrium, but also does not depend on Qi and Pi. So basically rho is constant. So the easiest ensemble is the one in which let's say the trivial solution to the Liouville theorem, to the Liouville equation or Liouville theorem constraint under the hypothesis of stationarity of the rho is that rho is just a constant, so it does not depend on Qi and Pi. Okay, so rho constant. And again, this would correspond to the case we were talking about at the beginning. We said, okay, this ensemble average is the sum of Fi over all the possible microstates by assuming that the distribution of the microstates is constant, in the sense that all microstates are equally probable. So saying that rho is constant means that all the microstates are equally probable. Which means, again, non ho scritto, rho constant. Which again, as I said before, reminds us the case in which we had n particle and k possible states, and we said that to maximize the entropy, and so to be at the thermodynamical equilibrium, the Gibbs entropy in that case, all the states were occupied with the same probability. Okay, so here there is the same, basically the same assumption. So rho is constant, so all the microstates are occupied, all the microstates have the same probability to occur. Okay. Now, considering the fact that Qi and Pi are limited in gamma, because there is a constraint on the energy, on the total energy of our system, that means that rho is a constant, but it cannot be constant over all the volume of the phase space. Otherwise, this will not be consistent with having a fixed volume and a fixed energy, right? So therefore, that means that rho is constant in a certain part of gamma, and is a constant different from 0, and it is 0. It is 0 outside this volume, or this part. Okay? So, to say in other words, you have a finite support of rho. Okay, so rho will occupy a certain volume of the phase space, and in that case, it is a constant. Outside this volume is 0. Okay, this corresponds to the choice of the microcanonicals, so to the microcanonical ensemble. Now we have to actually find a way to compute rho which basically means how to, because it is the same apart from a normalization, how to compute the volume of gamma in which rho is different from 0, and inside that volume this is constant. Now, to do that, we have to make the following trick, and then at the end, after that, I think I will close the lecture for today. So, strictly speaking, we said before that the system, the trajectories move on a hypersurface, which is determined by the constraints on the energy. So, we say the Hamiltonian is equal to the energy, and therefore this constitutes the equation of a hypersurface in the phase space. So actually everything is on this hyperface, but that is basically, first of all, difficult to compute. Secondly, is not really realistic to imagine that the energy is a certain number and without any error. So actually what we will do is to imagine that actually the trajectories are not moving exactly on a surface, but most likely or most reasonably on a layer, which then occupies a volume in the phase space. This layer being determined by a sort of uncertainty on the energy, which is a finite but small, so which is a small quantity delta, okay, an infinitesimal quantity delta. Okay, so instead of imposing H equal exactly coincident with the energy, what we will do, what is the standard way to do this calculation, let me change page. We will do the following. We have a sort of uncertainty. So E has an uncertainty delta, which is of course small with respect to E, and therefore H is not equal to E, but H is limited by E plus delta divided by 2, for instance, and a E minus delta divided by 2. So this is our constraint or our relation between H and E, which means also that rho is constant in the portion of the phase space for which H is between E minus delta half and E plus delta divided by 2. Okay? In the region or in the portion of gamma in which, or determined, if you want, by the condition E minus delta half less than H and E plus delta alpha. And rho is 0 elsewhere. Okay? So let me summarize. We know that in principle, all the points, all the trajectories moves along a hypersurface, which is determined by the constraints that Hamiltonian is equal to the energy. But then it's difficult to compute volumes, because you have a hypersurface. So it's much better, much easier to compute a portion of the phase space, and so introduce a layer, actually not a hypersurface, but a layer, which also corresponds to the fact that the energy is not exactly fixed, but you can have a sort of uncertainty on the energy. Now it is easier to characterize the ensemble, the microcanonical ensemble, which is this rho, which is constant in a certain portion of the volume of the phase space, provided by this equation, by these inequalities, whereas it is 0 outside, and which is the volume occupied or by the rho. Well, I can call it, we can call omega this quantity, which is the integral over all the phase space of rho d3n p d3n q, which is the integral of rho over the phase space, and which is basically, since rho is constant, this quantity here is proportional to the volume in which rho is different from 0. No? Rho is integrated in this integral over all the phase space, but since rho is finite in some region and 0 outside, this omega, which is this integral, must be proportional to, apart from a constant of normalization, to the volume in which rho is different from 0. Okay? And the statistical averages, that the ensemble average that we were saying before, are of course determined by the following definition. I have the integral over all the phase space of rho on here I have the f of qi pi d3n p d3n q, and here you have the integral of rho of 3 d3n p d3n q. Okay, where rho is a function, it depends how to normalize. In this respect, rho is a function of pi or qi, and basically it's a sort of theta function, if you want. Okay, it's 0 outside a certain volume and is different from 0 inside a certain volume. Okay, and so the average ensemble will be the following. Now I will close for today. The next time what we will do is basically to compute the volume of phase space that is in which rho is different from 0. Okay, so the next time we will compute this omega. Okay, which correspond, apart from a proportionality factor, to the volume of phase space occupied by the microcanonical ensemble. And after computing this integral, we will use again, so this region, we will use again the entropy of Boltzmann, and to compute the entropy of an ideal gas. Okay, so now it's 1, and I think it's better to close. If there are no questions, I close. Just wait maybe 1 minute if there are questions. So if not, I see you on next Thursday. Ciao ciao.
Arrivederci.
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 Arrivederci, grazie.